Problem number 14. A disk of a moment of inertia I, mass m and radius r has a cord wrapped around it tightly as shown in the diagram. The disk is free to slide on its side as shown in the top-down view. A constant force of T is applied to the end of the cord and accelerates the disk along a frictionless surface. After the disk has accelerated some distance, determine the ratio of the translational kinetic energy to total kinetic energy of the disk. Solution. First, we can write translational and rotational equations for motion of this disk and find what is acceleration and angular acceleration. Acceleration will be F over m and angular acceleration Fr over I. After time t, we can find what is velocity and what is angular velocity for this disk. After that, we can find what is translational kinetic energy, this one, and what is rotational kinetic energy, this one. And last step to find what is this relation between translational and total energy. The answer will be I over mr squared plus I, which is answer D. Problem number 15. The maximum torque output from the engine of a new experimental car of mass m is tau. The maximum rotational speed of the engine is omega. The engine is designed to provide a constant power output P. The engine is connected to the wheels via a perfect transmission that can smoothly trade torque to speed with no power loss. The wheels have a radius r, and the coefficient of static friction between the wheels and the road is mu. What is the maximum sustained speed v the car can drive up a 30 degrees incline? Assume no frictional losses and assume mu is large enough so that the tires do not slip. Solution. The main idea is a formula for power. If the force between wheels and incline is F and the speed of vehicle is V, power will be force multiplied by speed. In our case, incline is 30 degrees. It means that the car must produce force F equal mg multiplied by sine 30 degrees. And from this formula we can find what is the speed. The speed will be 2p over mg, which is answer A. Problem number 16. An object of mass m1 initially moving at speed v0 collides with an object of mass m2 equal alpha m1, where alpha less than 1, that is initially at rest. The collision could be completely elastic, completely inelastic, or partially inelastic. After the collision, the two objects move at speeds v1 and v2. Assume that the collision is one-dimensional and that object 1 cannot pass through object 2. After the collision, the speed ratio r1 equal v1 over v0 of object 1 is bounded by next inequalities. Solution. If we have absolutely elastic collision, we have energy conservation and momentum conservation, and these equations give us this relation r1, which is equal v1 over v0, equal 1 minus alpha over 1 plus alpha, and R2, which is V2 over V0, equal 2 over 1 plus alpha. In our case, object M1 more massive than object 2. It means that alpha less than 1 and the first object still moving in the same direction. In case of absolutely inelastic collision, this ratio must be V1 over V0, which is 1 over 1 plus alpha. Here we have a momentum conservation, and both objects move together. It means that in case of absolutely elastic collision, the first object moving with the minimum speed, and in case of absolutely inelastic collision, this first object moving with the maximum possible speed. So from these conclusions we can find that correct inequations will be R1 between this one and this one, which is answer B.